Hello, Mr. Claudia here, and today we are going to learn, well, the last derivative rule for a while, the chain rule. And this is also kind of the most difficult one, so take your time as you go through it. Really, the basis for the chain rule, before I show it to you, is that it helps us find the derivative of composite functions. Now, you remember composite functions, fog at x? Remember, we don't really like to write it that way. We like to write it as f at g at x. When we learn this, one of the reasons why we teach it to you is because it is helpful for understanding the chain rule. The chain rule allows us to find the derivative of this situation, the derivative of a function within a function. So here we go. Chain rule, derivative of a composite function. If I have a function, which is a function inside a function, the derivative is, now look at this, it's the derivative of the outside function with respect to the inside function times the derivative of the inside function. And that's one way of writing it. We're going to talk about this. Now, Leibniz, there's this other, like most of calculus was developed by Isaac Newton, but concurrently at the same time in Germany there was a German mathematician, Leibniz, my German is not very good, but he was also working in developing calculus. He developed much the same but different notation. Now you've come to know Leibniz notation, dy dx. It's a different way of writing the derivative. And there's an important way of looking at chain rule questions using his notation. So if I have y, which is a function of u, and u, which is an interior function of, which is a function of x, then dy dx, the derivative of y with respect to x, is equal to the derivative of y with respect to u times the derivative of u with respect to x. These are both the same thing. Now I know this is confusing and probably makes no sense, but as we're going to start going through examples and hopefully it'll become more clear. First of all, let's do what we always do, where we think about this in words. The derivative of a composite function is the derivative of the outside function with respect to the inside function times the derivative of the inside function with respect to x. So again, that is it in words. Again, it probably doesn't make too much sense just yet, but we'll start working through it. For now, I want you to appreciate the idea of the inside and outside function. For this composite function, g is the inside function, f is the outside function. So let's start by, we're going to get comfortable breaking down functions into outside and inside functions. Let's start with the Leibniz notation, because that might help us understand a question like this. First of all, can you appreciate that y equals root 2x squared plus 3? This is actually a composite function. The outside function is the square root of u, square root, right? That's the outside function. Into that, we've subbed 2x squared plus 3. So you can imagine this is the inside function that exists inside this outer function. So this question, we want to know the derivative when x equals 1. Well, let's write out that formula, that Leibniz notation. The derivative of y with respect to x is equal to the derivative of y with respect to u times the derivative of u with respect to x. Now, I need to figure these things out. So let's go over here for y. Y was equal to the square root of u, which is really u to the half. So if I want to find the derivative of y with respect to u, that means find the derivative as if u is my variable, right? It's usually dy dx, but this time it's dy du. So I need to differentiate with respect to u. So that's easy. The half comes down, and I end up with negative half here. So if you want to be a little cleaner about it, I end up with 1 over 2 root u. Now, I also need the derivative of u with respect to x. Well, u was defined as 2x squared plus 3. Now, let's take the derivative of u with respect to x. Well, the derivative of this is 4x. So now I have these two things and I can sub them in. So I'm just going to draw some arrows to show what I'm doing here. So now I end up with 1 over 2 root u times 4x. Now normally this would be a problem. You can't have an answer with an x or with a u in it. So I should technically sub in u is equal to 2x squared plus 3. So I end up with 4x over 2 root 2x squared plus 3. There's my derivative. And now I wasn't actually interested in the derivative. I want to know the derivative when x equals 1, so I can just sub in my values. X equals 1. So that would be 4 times 1 over 2 times root 2, 1 squared plus 3. That's 4 over 2 root 5. So I end up with 2 over root 5. Cool. So that's Leibniz notation. Note how you took a complicated function, you broke it down into an inner and outer function, and then you used the formula we gave you. You had to find two derivatives and you multiplied them together. We got an answer. So there's some practice. I want you to, again, this is not in your textbook, this is more of a, IB doesn't emphasize this too much, but it is something that we emphasize in the regular grade 12 program. So can you use the chain rule with this Leibniz notation to solve these functions within a function? And we've sort of broken them down for you already. And there are the answers over there. Now, one kind of classic IB question you might get is you have a composite function h where f and g are differentiable. If this is g, g prime, f prime, what is the value of h at -1? Sorry, what is the value of h prime at -1? This is a crazy question because there's no function given to you. That's why it's like very odd to look at. H at x is equal to fog at x, which I can rewrite to make it a bit more easy to understand. Now, my definition of h prime here is, again, this is we're getting into the other definition here. It's the derivative of the outside times, with respect to the inside, times the derivative of the inside. So that's going to be the outside with respect to the inside times the derivative of the inside. Now watch how this works. This is going to be f prime. Oh, well, first of all, we were looking for h prime at -1. So I'm going to change all the x's to -1. Now, let's watch how this works. G at -1. Oh, that was given to me. It's 2. So this is really f prime at 2 times g prime at -1. And again, both these things are given to me. F prime at 2 is -4. G prime at -1 is 3. So my answer is -12. This is kind of this is an odd question, but it's a quick one. You can see how you really have to understand how to apply the chain rule. Okay, let's turn the page. Alternatively, The other way that we can look at the chain rule is to do it in line, and this is where this is kind of the alternate method of doing it, where we use the kind of more standard way that's been written. But I'll show you the technique. So you have an outside function. Let's imagine that this is, well, if you look at this, you should see an outside and inside function. This is something to the power of 8. So that's my outside function, something to the power of 8. And then there's an inside function, which is x squared minus x plus 2. So I want you to imagine this, not as some crazy expression, but imagine this as a function within a function. So you have, say, y equals h or something to the power of 8, which is my outside function. And then that is where h is equal to x squared minus plus 2. That's my inside function. If you can imagine, I've subbed this expression into this expression. So the way I find my derivative using the chain rule is you take the derivative of the outside function with respect to the inside. So if I have my outside function, which is something to the power of 8, what's the derivative of it? Well, that's product rule, that's power rule. The 8 comes down, I write out that something, and then I subtract 1 from the coefficient. Right? The derivative of something to the power of 8 is 8 times the something to the power of 7. Then I need to do my chain rule. I need to take the derivative of the inside function with respect to x. So x squared minus x plus 2. It's a little poor space management. But this is the derivative of the outside with respect to the inside, and this is the derivative of the inside with respect to x. So now this becomes 8x squared minus x plus 2 to the power of 7. And this becomes the derivative of this, which is 2x minus 1. So I end up with, okay, I'm not going to touch this, but the 8 can multiply into this. So I end up with 16x minus 8 times x squared minus x plus 2 to the power of 7. And there it is. So that is the chain rule, and it makes our head spin a little bit. Again, the important thing is if you can imagine this as something to the power of 8, then you just take the derivative of something to the power of 8, which is 8 times something to the power of 7, but then don't forget to take the derivative of the inside. Whew. Okay, let's do a question like this. Now this is e to the power of 2x, and you may think that doesn't look like a chain rule question, but it is, right? This is the, how can I write this? I want you to imagine right? I have f at x is equal to e to the power of something, e to the power of h, and then the h is equal to 2x. Right? So I've subbed 2x into e to the something. So when I find the derivative of this, well, that is the derivative of e to the something is just e to the something. So it's still going to be e to the 2x. And then I need to multiply it by the derivative of whatever that something is, which is the derivative of 2x. The derivative of 2x is just 2. So I end up with 2e to the 2x. Okay, this is not easy, right? It looks easy, it's not easy. It's tough to see this as a function within a function. And I think one of the things that students get lost in is they say, well, wait, does this undo everything I've already learned? And it doesn't really. Like, consider f at x is equal to just e to the x. When you find the derivative of this, you're finding the derivative of e to the something, which is just e to the something, times the derivative of that something, which is x. Now, what's the derivative of x? It's just 1. So this is actually just e to the x. So even though, like, we're teaching the chain rule now, all the questions we've given you so far have conveniently not have chain rule, because the thing that is, you know, the interior function has always been x. So it's always come out to be a derivative of 1. We've conveniently only given you these questions. Now we're giving you functions within a function where it's not necessarily an x. Here it's a 2x. I hope I was clear in that. I just had a note which was right, and hopefully we can, if you went back to all of your previous lessons, this would make sense to you. Like, you would be okay with the fact that we haven't shown you chain rule until now. Okay, let's do another example. Let's do this one. First of all, I don't like it because it's got a negative exponent and a rational exponent. So I'm going to rewrite it as 1 minus x squared, or sorry, x to the 4, to the negative 1/3. Okay, that's a function. Actually, it's a function within a function. This is, again, if you want to imagine, and it's useful to imagine, this is f at x is equal to something, h, to the power of negative 1/3, where that something is equal to 1 minus x to the 4. That's classic chain rule. It's a composite function. So, to find the derivative, here we go. F prime at x is equal to the derivative of something to the negative 1/3, which is negative 1/3 times that something, 1 minus x to the 4. And then actually have to subtract 1 from the exponent. So it'd be negative 1/3 minus 3/3. But I'm not done. Chain rule. I have to also take the derivative of the thing inside my bracket, which was 1 minus x to the 4. Don't forget the chain rule. Now I just have to simplify, right? Oh no, sorry, I have to still do this derivative. So I have negative 1/3, 1 minus x to the 4. And I have negative 4/3. And then I have the derivative here, which is negative 4x to the cube. Now the calculus is over. I should just clean up the question. So the negatives cancel out. I end up with 4x cubed over 3, 1 minus x to the power 4 to the power 4/3. It's going to be messy, but I just got rid of all the negative exponents. Then make sure I combine my like terms. Now that we've learned the basic chain rule and we're experts with the chain rule, now you can expect to see some questions that are a combination of chain rule and product or quotient rule. So your nightmares are really going to become true. Let's look at this question. So when you look at this, you should immediately think, okay, well, this is a product rule, right? Like I have my first function here and I have my second function here. So I need to do my whole product rule procedure. So here we go. I have dy dx is equal to, and let's write this all out. So I have the derivative of the first function times the second function, don't forget those exponents, plus the first function times the derivative of the second function. So that is called product rule. You guys are great with that. Now we just have to do the derivatives, the instructions, which like take the derivative of this. But look at this. This is the derivative of something to the power of 4, right? A function, u squared plus 3, inside another function, u to the power of 4, or whatever you want to call it. So when I do this derivative, I have to make sure I do the chain rule. So what's the derivative of something to the power of 4? Well, it's 4 times that something to the power of 3 times the derivative of the inside, of the something. So that is 2x. Your nightmares come true. So this is the outside function. And this is the inside. And then don't forget, there's still this mess here, 4x minus 5 to the power of 3. Then we have, what did I write here? Oh, plus x squared plus 3 to the power of 4. Now, can we find the derivative of the second expression here? Well, okay, so what's the derivative of something to the power of 3? Well, it's 3 times that something times the power of 2 times the derivative of the thing, which is the derivative of the inside, which is 4. So I have my outside and my inside. So that is the chain rule, has to be applied. So there's possibilities for error everywhere. Messing up the product rule, then messing up the chain rule. Okay, now the next thing I have to do is clean this up, right? Like technically the calculus is over. And if you had a question that said don't simplify, you'd be done. If you had a question that said figure out what the derivative is at x equals 1, you would be done. You just sub in x equals 1 now. But this question was asking us to express your answer in simplified factored form, which means that I'm going to try to factor out the common factors. So the first thing I'm going to do is clean this up a little bit. So 4 times, these are all being multiplied. So 4 times 2x is 8x. X squared plus 3 to the power of 3, 4x minus 5 to the power of 3, plus, what about here? Oh, there's a constant, 3 times 4, which is 12, x squared plus 3 to the power of 4, 4x minus 5 to the power of 2. Don't forget your exponents. Now, let's simplify this into a factored form. So I need to factor out anything that's common. So let's start with the numbers. What's common in the constants here, or these coefficients? The number 4. Okay, and is there anything? Now let's look at the different expressions. So I have an x squared plus 3 and an x squared plus 3. I actually have x squared plus 3 to the power of 3 and x squared plus 3 to the power of 4. So that means I have x squared plus 3 to the power of 3. I can factor that out. That's in both of them. Finally, 4x minus 5. I have that 2 of them here, 3 of them here, so I can factor out 2 of them. So now let's see what's left over. So remember, what is factoring? Factoring means you're taking something common and you're dividing it out of both terms. So if I take this first term and divide it by 4x squared plus 3 to the power of 3, 4x minus 5 to the power of 2, let's see what's left over. Well, looking at the coefficients first, I end up with just 2x left over. The x squared plus 3 to the power of 3 divided by x squared plus 3 to the power of 3, those divides out completely, so it's gone. And then 4x minus 5 to the power of 3, dividing out 4x minus 5 to the power of 2. Well, if you imagine I divide, I'm subtracting the exponents. So all I'm left with now is 4x minus 5 to the power of 1. Okay, next term, plus, okay, now I'm going to divide this factor out of this. So the 12 divided by 4 is 3. X squared plus 3 to the power of 4 divided by x squared plus 3 to the power of 3. That's just x squared plus 3. And the 4x minus 5, it divides out. So I'm done. Whew. Now, I'm not going to touch this cubed or squared. Those I'm just going to leave because like that's just going to get messier. It's already been factored. So all I'm going to clean up is what's in my brackets here. So I have, what do I have here? Do I have room? Okay, so 8x squared minus 10x plus 3x squared plus 9. So my final answer is 4x squared plus 3 to the power of 3, 4x minus 5 squared, and then this bracket becomes 11x squared minus 10x plus 9. And that is simplified factored form. Now I will make a note and just say that traditionally this simplification is not needed on IB tests. So on a Mr. Claudia test, it's possible I could ask you this, but on IB tests, they don't have time to ask you questions like this. They're probably going to have a simpler version, or they're just going to get you to stop here. It's very rare that you have to do this. And I find when I teach this concept, this is the thing that stresses out students the most, which is the simplification. So lucky for you guys, you don't have to worry about it too much. Okay, let's do 2 more questions here. I have y equals ln. So look at this question. A function within a function. My outside function, if you want to imagine, y is equal to ln something. Let's call it ln h, where h is equal to x squared plus 1. Oh, sorry, it's x over x squared plus 1. Oh my god, this is horrible. So I have an inside function, outside function. My outside function is ln. So let me do my derivative. dy dx is equal to, oops, let's write this something like this. So what's the derivative of ln something? Well, it's 1 over that something. So that 1 over x squared plus 1 times, chain rule, the derivative of that something. Wow, this looks like a nightmare. And look how much little space is left. So first thing, 1 divided by this, well, that just means flip it upside down. X squared plus 1 over x. Okay, that's looking better already. Now, what's the derivative of x over x squared plus 1? Oh, facepalm. I have to do a quotient rule here. So, let's do it. Derivative of the top is 1 times the bottom minus top times derivative of the bottom, which is 2x, all over x squared plus 1 all squared. Luckily, we spent so much time on quotient rule. Now, I just have to clean it up, and you'll see it's not terrible. Like, the x squared plus 1 squared and the x squared plus 1, I mean, technically these cancel out. So I'm left with x squared, oops, sorry. So 1 over x, and here I have x squared plus 1 minus 2x squared over x squared plus 1. And what do I end up with then? Negative x squared plus 1 over x times x squared plus 1. Oof. So, chain rule, but then wrapped up in the chain rule was a quotient rule. One final question. I have f of x is equal to e to the x to the 3 times this function. So hopefully you're looking at this and you're saying, hey, there's a first function and there's a second function. This is product rule. So I'm going to have to do my product rule. So again, I'm going to write this whole thing out. First of all, take the derivative of the first thing times the second thing plus the first thing times the derivative of the second thing. Okay, well, not so bad. Now, what's the derivative of this? This is where your alarm bell should be going off. Hey, this is a chain rule question. Because this is e to the something, and then the something is x to the power of 3. So even though e is really easy, right? E is an easy one to take the derivative of. You got to be very careful. So this is actually e. So it's, what's the derivative of e to the something? Well, it's e to the something still. Times the derivative of that something. Again, I find this to be one of the harder ones. The e is the one where you tend to miss, you make mistakes and miss the chain rule. Okay, times whatever I had here. The rest is kind of easy. The derivative of this is 6x. Okay, so now, I guess I have to take this derivative, so I end up with e to the x cubed times 3x squared times 3x squared minus 2 plus 6x e to the x cubed. Now, technically what I should be doing is expanding. Yeah, I guess I'll expand first. So I'll distribute that. So I'll end up with 3x, no, that would be 3 times 3 is 9, x squared times x squared is x4, e to the x cubed, minus, okay, 6, x squared, e to the x cubed, plus 6x e to the x cubed. There is a common factor here, which is, well, these are all divisible by 3. X e to the x cubed. So let me factor that out. When I do that, I'm left with 3 x cubed. 3, okay, it's minus 2x plus, that's just 2. So I factored this, I divided each of these terms by that factor, and there's my final answer in factored form. Whew, what a doozy. So sometimes I do that in 2 days. I guess you guys are going to do it in 1 day. Hopefully it isn't too hard on you. Your homework is going to be first of all the other side, the other page, then page 217, number 1 to 10, and 219, number 1 to 14. Chain rule is definitely the hardest thing in this chapter, so good luck. Oh, sorry, I did just want to say before we finish, look at the different possibilities you have here. This was product rule first, so I used my product rule, and then in doing so I had a chain rule to deal with. This question was chain rule first, then I had the coefficient or the quotient rule to deal with. So there's different ways you can have it. You could have chain rule that leads to product rule or product rule that leads to chain rule. Just make sure you're methodical and you do them in the right order. Depends on how the function looks. That's why we've practiced writing the thing out. Anyways, good luck with your homework, and we'll see you next time.